Hello, my name's Adrian, and today I'll be showing you how I've built my embedded device project, which is a bicycle GPS tracker that also collects data about proximity to other obstacles on the road and hopefully will give us insight into the safest routes for cyclists. Bikes are my main mode of transport, so I want to use this project to explore ways we can use embedded technology to improve safety on the road. Giving bicycles enough space is of key importance to safety. So the basic idea is that when you're cycling along and a car or obstacle gets within a meter of you, that's a warning sign that we're either not providing adequate bike lanes or drivers aren't really respecting the space needed to safely use our bicycles. So far I've prototyped a portable device which tracks the bike and sends proximity data, while a second device in the system connects to that data to display a dashboard in the home showing a heat map of activity. I originally started this journey using a particle photon, much like everyone else, figuring I could connect it to my mobile hotspot using my iPhone and use a library called Google Maps Device Locator to track location. This library lets you find a photon's location by looking up Google data of known Wi-Fi points and then triangulating the position depending on which Wi-Fi points the photon can see at the time of reading. Now this worked pretty nicely in my first prototype at home, but unfortunately once I took it for a spin around the block it just didn't give anywhere near enough accuracy. So for this project I've ended up using a particle electron, which is similar to the photon but it's more geared towards mobile projects. Rather than Wi-Fi, it works on 3G, and it also has a ready-made JST connector for connecting a LiPo battery. As a bonus, it also has a lot more GPIO pins. The other piece of gear which has made a huge difference in this project is the particle asset tracker kit. Now this is basically the Electron kit, but it has an added asset tracker shield, which is a GPS module. Although I think cell tower triangulation would have done a reasonable job, I feel that dealing with too much location inaccuracy would have made the project kind of pointless, since my project relies very much on accurate locations to give us any kind of meaningful data. So the hardware we're going to need is a Raspberry Pi to run the home dashboard, a particle electron, the asset tracker GPS, 2 ultrasonic sensors, LEDs for giving visual feedback on the road, and a LiPo battery. Now just a side note on that battery power, I've come across a problem with powering my project using only the LiPo battery. The ultrasonic sensors use a 5-volt signal, so it looks like the battery isn't providing enough power to get those working at the same time as the asset tracker. To keep me running, I've just been plugging in my laptop as a power source, but I've ordered this 5-volt step-up voltage regulator, and hopefully once I get that connected I should be able to provide a bit more current. Another note, I'm actually powering the sensors through the VIN pin on the Electron, which provides about 4.8 volts of power. I was worried about feeding that signal back into the 3.3 volt pin on the Electron, because I'm pretty cautious of frying any of my equipment and I'm not that experienced working with different voltages. So I did a bit of research on that, and in my first prototype I built a little resistor circuit. You can see down here with the couple of blue resistors, and the idea of that is to reduce the volts from 5 volts down to 3.3 volts. So I did this by using an online calculator which helped me to know which resistors to use, and it actually worked pretty well. And I happen to also have a logic level converter lying around which does a similar job. This is this little red thing here, and what they do is they can convert signals as well. So this one can convert 5 volts to 3.3 volts as well. This was a bit more of a challenge, this one, because I actually had to teach myself how to solder. Unnerving, it was something totally different, but I was really happy because it's something that I wanted to learn, and I'm really pleased that I was able to add that to my tool set. If you get a chance to have a go at soldering, I recommend it, because it's once you have stuffed it up a few times, it's not that difficult. So after I got all this up and running, funnily enough, I stumbled across a vital piece of information in the particle datasheets. It turns out that most of the pins on the photon and the electron are 5-volt tolerant, as long as you set them up using regular input mode. So that turned out to be a bit of a wild goose chase, but you know, these things happen, and I learned how to solder along the way. Alright, here's a bit of a look at what comes in the Electron asset tracker kit. So it's got this little box here with all the usual documentation and that kind of thing. This is a weatherproof case for it, which is actually really cool. It comes with screws so that you can mount that in there, and I've already screwed in my GPS module into the bottom of that. This is the antenna that is for receiving a 3G signal when you're out and about, and that just screws into the top of this, or pops into the top of this electron here. There's a JST battery connector on the right here, and that's your regular USB, and then on the flip side we have a spot there for inserting the particle SIM card, which is really handy. Now they provide a service for mobile data. It's $4 US dollars per month for a megabyte. Now that doesn't sound like a lot of data, but a very simple particle publish event is around 128 bytes. So you should be able to publish thousands of events per month with that data. Even so, one thing I learned is that it's good to use short event names in your publish events to avoid using unnecessary data. Now what else have we got here? We've got the, this is the LiPo battery, which is nice, and that's about it. Now I'm glad I didn't start ordering batteries for my photon originally, which I was about to do before I came across this kit. So one thing I've learned is to just do the minimum possible solution first before you start ordering heaps of gear. The best feature of this, of course, is the GPS module, which I've now got mounted inside my weatherproof box, and I'll just show you what the lid looks like. That's nice. Would be all sealed. So what you do is you take your electron and you just line it up with the pins and push it in, and there we go. And over on the right hand side, that little silver square there needs to face the sky, and you can also attach an external antenna if you want a super good signal, and there's also a satellite fix LED here, which gives us some indication when you've actually got a GPS fix. Now one of the key challenges I have here is weatherproofing this thing. Like I've got this really nice weatherproof box, but that only covers the expensive parts, and it's not really geared towards having wires sticking out everywhere. This is really just a prototype product, and I can only do so much, but this can be a bit frustrating. We're expecting some rainy weather next week, so I've been madly cycling around town collecting data and looking like a complete lunatic with this crazy contraption stuck to the front of my bike with wires going everywhere. The other thing I found is GPS really does not work too well indoors, so sometimes while I'm coding I need to sit out in the fresh air, which isn't so bad, I guess, up here in Queensland. Okay, so here's a little tour of the circuit that I've built. Firstly, at the back here we have the electron, which is running the whole thing. It's mounted into the weatherproof, or the bottom of the weatherproof case. And then of course we have a LiPo battery which is plugged in. Now for the other parts, on each side I have an ultrasonic distance sensor which is plugged in, and I also have a red LED which is going to give us an indication of when the distance fires, so that will turn red just to show me that something's happening. Exactly the same on the other side. And in the middle I have kind of a central breadboard just to make everything a little bit neater, and also so I've only got one output for the power and for the ground from the electron, and I have two LEDs in the middle here. One indicates when we have a GPS signal, and the other one indicates when the accelerometer has detected movement. And both of those things are requirements for this system to operate, and I wanted to add the LEDs in so that I could see what was going on behind the scenes, because otherwise it just looks like nothing's happening. Okay, here's a quick demo of my prototype. We have the electron sitting in a crazy looking box, and I have a green LED which indicates the GPS is functional. Next to it I have a blue LED which is not lit at the moment. That indicates when the accelerometer has detected motion. On each distance sensor here I have a red LED that will fire when it detects motion, and it doesn't work when the bike is not moving, but if we give this a bit of a shake we should see the blue LED is on, and then the red LED starts firing, and it turns back off when the bike stops moving. So if we move that again, and there we go, and that's all working, and now we stopped, and we want that to go to sleep. And this is because if we park the bike somewhere, we just want to be able to walk away without worrying about switching the system off or making any false positives. Alright, here is my bike, and as you can see I have a very rough prototype of my distance set up here. So I've got the electron sitting in there. This all needs to be weatherproofed, but at the moment this is my rough version, and I've got two distance sensors either side ready to go, and that's trying to get a 3G connection right now. So this is the code that I've got running on my electron. Now this runs multiple distance sensors in conjunction with the asset tracker library. There are quite a lot of physical elements working together here. We've got the GPS, we've got the accelerometer, and we've got two distance sensors. So there was a lot that could go wrong, but I've started out really simple, and I've tested each feature in isolation. And then as I went along I made it more complicated as I confirmed that each component was working. One of the early challenges was making the distance sensor work in tandem with the GPS, because I originally had a sleep command, which is a pretty normal thing to do, to take readings every second. This didn't work all that well with this update GPS function right here, because that actually likes to run continually inside the loop. Sleep is actually a blocking command which stops anything else from running for the period that you specify, and both the GPS and the accelerometer both like to take readings each time the loop runs. So where I need a delay, I've actually used this function here which is called milliseconds. So what this does is gives you the number of milliseconds since the program started running. We can then set timestamps, like I've done here with the last bump at. And so what we can do then is compare the current timestamp to a flag that you set, and then check if it's greater than the delay that you want. So the reason I'm using it here is because I actually want to keep track of when was the last bump that the accelerometer has detected, and I wanted to keep a flag or store that into a variable here, and then do a comparison so that we can actually send the system to sleep, which I'm doing over here. If the accelerometer hasn't detected any motion for 5 seconds, I just want the system to go to sleep, and not to, like for example, if I park the bike against the wall, I don't want to be sending off all these data events to say that there's some kind of proximity event happening. So that's what I'm doing there. So that catches anything like that, and then we have an else condition which then goes through and starts firing off the distance sensors. So what I don't want to happen is to start logging or trying to log any data if we don't have a GPS fix. So I've made a condition here: if there's a GPS fix, turn on the LED and then start reading from the sensors. Otherwise, just turn the LED off and ping the serial saying that we're waiting for a satellite fix. Now down here I've just got a couple of utility functions that I'm using, so when a distance sensor sends out a a little sonic pulse, it sends one out and then it receives one back in, and then it takes it measures the amount of time that it took for that signal to come back. So in order to get a distance from this, we actually need to do a bit of a calculation. So what we do here is quickly trigger off the sensor, and this pulse in here will give you the time that it took for that to come back. And then we've got a calculation here that does accounting for the fact that sound travels at 0.0343 centimeters a second, and we can cast that into a double and then return the distance, accounting for the time that it took to go out, bounce off whatever obstacle is out there, and then bounce back into your sensor. Another couple of functions here I've got which fire the appropriate sensors. What I did add for fault tolerance is a proximity trigger. I want to sense the distance continually, but I don't want to necessarily fire off an event unless we've had confirmation, because we can often get false positives. So there's a true positive delay here. So every time you get a positive, you increment the count. If the count equals a true positive delay, which I think in this case I've got this set to 3, so I want 3 positives before I will confirm that as a real positive and then send the data. Okay, so then we've got the same thing down here for the second sensor, and then another function at the bottom here which takes the distance that's been read. It needs to check whether there has been a publish in the last second, because one limitation that we're working with is that the particle service won't let you ping it or publish events to it more than once per second. So I've done this timestamp comparison here again, and just checking whether that is greater than the limit, and only proceed if that's true. So we convert our distance to a string, and we also read the latitude and longitude from the asset tracker here, and then I've got that put into a string, and then I'm publishing that data. And like I said earlier about saving data, I've just got this event called G, and just keeping that string as short as I possibly can. So this is going to be a string that has the distance, a comma, the latitude, a comma, and the longitude. Okay, and this is a demo of my heat map dashboard, which we'll be running on a Raspberry Pi. And now this shows us all the proximity events as points on a map. This is pulling in the data that we logged to ThingSpeak via a particle event, and I've used color coding to indicate severity, with red indicating an event which is closer than a meter, which is the recommended minimum safe passing distance. 1.5 meters is orange, and 2 meters is yellow. I've also added a blue arrow to indicate the last known location of the bike, which is a bit of a bonus security feature. It's also a nice feature for the family at home, because they can see exactly where their loved ones are up to when they're commuting home from work. All this is currently running on a Node server, and I'm also planning on setting up a web server, which means we can access the dashboard from anywhere. And this is what I've got going on behind the scenes. This is a simple JavaScript script which is going to be running a Node server, just serving up a simple index HTML page, which I plan on making accessible from anywhere. And this is the main script which I've got. This is using a couple of different APIs. Firstly, the Google Maps API, and secondly, the ThingSpeak API. Now, ThingSpeak, you can use the API to call and fetch any data from any channel, and I've combined this with the Google Maps JavaScript API to build the web page that displays all data points on a customized Google map. So what it's doing here is fetching the data from the API, and I'm doing that on a set interval, and once it retrieves that data, then it loops through it and plots each point, pulling out the latitude and the longitude and plotting each point on the map. And that pretty much sums it up. Overall, I've really enjoyed this project so far, in particular making the connections between software and hardware in a way that's hopefully useful to everyday people. Thanks for listening, and I look forward to updating you and letting you know how it goes.